the second lecture on electric dipoles. Today we shall consider what happens when an electric dipole is placed in an existing existing electric field. The electric field may be uniform or non-uniform. For non-uniform electric field, we write as vector E vector as a function of R. We are for the timing, we are considering static field, so there is no time dependence. A dipole with minus charge Q placed at A and plus charge Q at B. The position of the center of the dipole is R with respect to some suitably chosen origin, and 2s is the dipole length. In that case, this R plus S is this vector, so this is R plus S vector. This R plus denotes that it is the position vector of charge plus Q with respect to O. Similarly, R minus is equal to vector R minus S vector is the position of charge minus Q with respect to O. Our aim is to find out what is the potential energy of this dipole when placed in an electric field, and the force acting on the dipole as a whole, and the torque. These three things we shall consider. So potential energy, coming to potential energy. Potential energy of the system. If we consider the potential energy U of the system, we express every quantity relating to the dipole, that is its potential energy force, will be represented with regards to the quantity referring to its center. So we call the potential energy. It is the potential energy of the negative charge plus potential energy of the positive charge. If phi is the electric potential, then it is at R minus. This is the potential energy of the negative charge. It is being placed at R minus, and this is Q phi E at R plus. Writing explicitly, this becomes Q taken common. This is minus phi E at R minus S, and this is phi E at R plus S. We want to express this potential energy in terms of the potential at the center of the dipole. So what we need to expand this. Let us consider this term. So phi E at R plus S, this can be written as phi E at X plus Sx, Y plus Sy, Z plus Sz. When we consider that vector S has its Cartesian component Sx, Sy, Sz. In the case of single variable, earlier we found that if we have a function like this, it can be expanded in Taylor series about x as f prime at x plus s square by factorial to f double prime at x plus higher order terms. Here we shall apply the same Taylor series expansion, but for this time you need to keep in mind that the function phi is a function of three variables. Keeping this in mind, we write first phi E at x, y, z. This corresponds to this term, that phi E at the point of expansion. Then change in phi E due to change in x only by an amount Sx. So this is given by del phi E del x at the point P, that means point P has the coordinate x, y, z times Sx. This corresponds to this term. plus del phi E del y at P times Sy plus, I am erasing this line, plus del phi E del Z at P times Sz plus higher order terms. So these terms, second and third order partial derivatives will be involved in it. So if we write this is actually phi E at vector R, and this term can be written as vector S times grad operating on phi E, and the quantity is evaluated at P. And if we neglect the higher order terms, this is the expression. So this is the expression of phi E at R plus S in terms of phi at R. Similarly, if we expand it for negative term R minus S, only thing is that it is phi E at R, and this S is minus, so this is minus phi E at R. So if we plug this 2 in this expression, we get Q. For the first term, we get with a minus sign phi E at R minus S dot nabla operating on phi E again at R. Since this is a theory correct up to first order partial derivatives, we are putting an approximation sign, and for this term we have phi E at R plus S times nabla operating on phi E at R. That's all. Now you see that this term gets cancelled and this 2 negative makes it positive, so this 2 term adds up. So this is twice Q S dot nabla operating on phi E at R. Remember that twice QS is P, in that sense it is P dot nabla operating on phi E at R. Furthermore, note that the field at this point, at the point P is governed by P phi at R is governed by minus grad of phi E at R. That means the different derivative has been carried out at R. In that sense, it is minus P dot E at R. This is the expression for potential energy of the dipole. This is the expression for potential in terms of potential energy of the dipole in terms of potential, and this is the expression in terms of the field referring to this point. Now come to the force that acts on this dipole. If we want to find out the force, expression for force, it is the force acting on the negative charge plus it is the vector sum of the force acting on the positive charge. So the force that acts on the dipole when it is placed in an electric field, it is the force on the positive charge plus force on the negative. So let me first write negative charge, then force on the positive charge. So negative force on the negative charge is minus Q times E at R minus S, and force on the positive charge is Q E at R plus S, because the positive charge is placed at this location. Again, our aim will be to express this thing in terms of the quantities with respect to the center of the dipole. In doing so, we have to expand this again in Taylor series, but for this time, remember that the function itself is a vector function. So similar expansion holds, only thing these will be replaced by the corresponding vector function. So the thing is that q taken common, for this term we will have minus e at r. This is the term, this term, or this term, minus s times nabla operating on e at r. Since this result is correct up to first order differentials, I put an approximate sign on. This is e at r plus s dot nabla operating on e, again the carried out at r. Again, these two terms gets cancelled and these two negative gets it positive. So the result is twice q s dot nabla operating on e, and this is e dot nabla operating on e at r. Note that if the dipole were placed in an uniform electric field, then the electric field will be a constant vector whose differentiation is 0 and no force acts on the dipole. Let us consider a dipole like this when placed in a uniform electric field. Then if this is with a positive charge plus q, then a force of q times E acts on this, and if this is with the location of the negative charge, then a force q times E acts in this direction. So these two forces, the field being uniform, these two forces equal and opposite and gets cancelled, and only a torque acts on a dipole which tends to rotate it, and the tendency will be to align the dipole in the direction of the field. So this is the expression for the force acting on a dipole there. So no force acts if E is equal to a constant vector. Now we will come to the third part, the torque that acts on the dipole. In doing this, remember the expression for E field over here and over here in terms of the quantity referring to the midpoint of the dipole. That will be required. And furthermore, the expression of the force. So I just write the conclusion. Force acting a dipole is P dot nabla operating on E at R. This is my conclusion. Now come to the torque. The torque that acts on the dipole, if we consider the torque acting on the dipole as viewed from this point O, the torque is the torque tau is the vector sum of the torques acts on this and the well and there. Now the torque on the negative charge plus the torque acts on the positive charge. Now torque on the negative charge is R minus cross it minus. So this is the position of the negative charge and this is the force on the negative charge plus R plus cross F plus. So if we write it in longhand, this is R minus S, this is for R vector, times E minus S minus Q times E at R minus S. This is for this. And from this part, this is U R plus S crossed by. Now, Q taken out. We adjust this negative sign, so we write it minus R plus S cross this part E at R minus S dot nabla operating on E at R. This is for this part plus R plus S E at R is dot nabla E at R. This is it. Now, since this theory is correct only up to the first order differential, we put an approximation sign over here. Consider when R is crossed with this is the negative part, this is positive part, so this cancels out. This S operating on this is plus, this is also plus. So we have 2Q S cross E. Now, if R is crossed with this is positive, this also positive, these two answer. This is negative and this is positive, gets cancelled. So we have again twice Q R cross this thing is P, the dipole moment P, so this is P cross E of R, and if we couple these 2Q with this is P, so this is R cross but this is the force, the total force that acts on the dipole. So we write it as P cross E at R plus R cross F. This is the net dipole, the net torque that acts on a dipole when placed in a non-uniform field. If the field happens to be uniform, so no force acts on it, and this is 0, and this part is the only contributor to the torque so far as the first order theory is concerned. The appearance of torque has been explained in the earlier example. Let me explain once again. This is for, if this is with the positive charge, this is the force on the positive charge, and this is the force on the negative charge. When the field is uniform, these two are equal and opposite, and so no translational force, but only a torque acts on this. If this is with the dipole moment, the tendency will be to align the dipole in the direction of the field, and this is expressed by the potential energy. You know that the potential energy is a minimum one when the dipole is aligned in this direction, because the potential energy is minus P dot E. So when the P is parallel to E, the angle between these two is -0, so the result is minus P times A. The potential energy is the minimum possible one. And this is the expression, general expression for the torque that acts on the dipole. By this, we end our lecture, a second lecture on dipole, which addresses what happens to a dipole when placed in an electric field. In this lecture, we haven't questioned about how this electric field has been originated. We have assumed that some electric field has been produced somehow and the dipole is placed in this field. Then its potential energy, force and torque have been calculated. In the third lecture on dipoles, we shall consider what happens when one dipole is placed in the field due to another dipole. That is, dipole-dipole interaction will be our subject in the next lecture.